Welcome back to my Johnny. As I told you, this is the award ceremony for the 2023 Galileo Galilei Medal Award. And before starting this ceremony, I would like just to say a few words about the place you are. I manage it. Okay, you are here. This is the Hill of Arcetri, a wonderful place. The best place in the world. This is the Department of Physics and Astronomy at the University of Florence. And in fact, actually, they devoted to an institute, the Galileo Galilei Institute for Terrestrial Physics, which is the adventure of the INSAT and of the University of Florence. If you go up here later, you will find an institute about physics, then there are just physical observatory, and in this way of the right, you find a place where you are. Namely, this is the GGI. That's not going. Okay, and this is the Galileo, the place where Galileo spent the last years of his last life. Il Galileo was a national monument till 1928. This is the place where you are. And it was Galileo convened nine hours of science. After the success of the trial of the Orioles, and it was confined here in Ireland. Although Galileo was confined, he received the visits of friends and men of science, and had this last year that his lifetime he spent plenty time with the Princess Salesiana evangelist church, and following their conversation of the great attention and vivacity. So, it is not those eyes on that say where the scientific need was aware. It's used for highlight research and advanced studies where rules such as the Galileo Galilei Institute for Terrestrial Physics. Maybe the bad is on the food. Just a little bit of history. The GTI is a research hub out the multidisciplinary from physics. It is dedicated organized and investing on the problems. One of them is and also PhDs for reversing the fundamental understanding of the universe. Topics like the GI activities covered all the topics of theoretical physics, from strict theories to particle phenomenology, astroparticle cosmology, statistical mechanics, and nuclear theoretical answers. The spirit of GTI activities to favor discussion and collaborations and with environmental and SCFCs. Absolutely. Or that it had other times that's always in the area. And that's just so this is a reference point in highlights research for international science. In 2008, the IR was not established as a Centro Nazionale BNFN for Advanced Study, in partnership with the University of Florence. And when the IR established the Schwer Center, I read the Galileo Galilei in honor of the Federal Organization. This medal is assigned every 2 years by a special selection. The one of our scientists in the 25 others years for the award has received the status in theoretical physics. The first lesson was one on the Senate. Or it was groundbreaking ideas in theoretical physics, and especially with the discovery of relativity, gravity, and ordinary quantum theory. It's far-reaching in junctions, structure, during the that year. 2021 was just was the end of the world gone. Well, it's something unknown, suppose the wing, and that's useless. With the fundamental understanding the sources of radiation by complementary analytical getting techniques, enabling predictions that are then confirmed by gravitational wave observations and are now key tools in this new branch of astronomy. Now, we are celebrating the third edition of the Galileo Galilei made in the world. And this time the medal went to the last Donald so for development of powerful methods for high places in a quantum field. I had an honor to open the ceremony for 2023 Galileo Galilei Medal Award. I'd like to thank the selection committee of this edition, Graciela Giannini, Juan Massina, Mike Pesky, Eliazia Razinovici, thank you for being here, and Mikhail Shifkin, the University Authority and the NSN for supporting the GTI, and all the scientists who have been contributing to its success. So I definitely opened the ceremony, and I try connect with the president of the INSN, Antonio Zoccoli, which unfortunately could not be here.
Hello.
No, it's not.
Ciao.
Ciao.
Oh, thank you very much. It's pity that I cannot participate in person as I did last time to this ceremony, which I like very much. Also because I am an experimentalist and I'm always happy to learn something from theorists. I'm also particularly happy for this Galileo Galilei medal, which has been assigned this year to these three scientists for their contribution in the development of methods on high order perturbative calculation in quantum field theory, and also for the fact that at the end we are expecting a result that are coming from a theories from new principle, but in this case is some way different. And the approach of Bernard Dixon and Kosover is a kind of new approach, at least in my understanding, and I really appreciated the way, the path they had found and the result that have been achieved. So I will be very curious to listen to the presentation from them, and I hope that this approach will open new horizon, new approaches, not only in quantum field theory, but also in other fields like gravitational waves, and will provide previsions which can be used by experimentalists in order to check the theory and to foresee unexpected effect in the physics. So thank you very much, and have a good ceremony. I will follow very carefully. Thank you very much, and thank you, Stefania, and apologies not to be there.
Thank you, Antonio. Thank you for this. Okay. And next time you have to be here, okay?
Of course, I will promise.
Okay. Thank you. Thank you very much. And now I want to call here the prorector of from research of the University of Florence, because as I told you, the Galileo Galilei Institute is a joint venture. So Deborah Berti, please.
Thank you, Stefania. Ladies and gentlemen, esteemed colleagues, friends, students. So it is my honor and privilege to welcome you today to this ceremony. And I think that as Vice President for Research of the University, and on behalf of our Rector, Alessandra Petrucci, who could not make it here, we are just proud of this prize, and what I would like to congratulate the National Institute for Nuclear Physics and the Galileo Galilei Institute for setting this up, for organizing and the prize and selecting. To our medalists, Professor Berger, Professor Dixon, and Professor Sover, I would like to send my words of congratulations. Because I was meeting motivation, so I'm afraid that in a physical chemist, I did not capture the subtleties of the motivation. But while I see that your achievements in the field are indeed remarkable. So to our students and some young people around, I would like to go to inspiration from the work or the achievement of the science that contributed to shape our understanding in such complex physical phenomena from a theoretical point of view. And as we done earlier, and I feel like I don't think we not run with the video in because we are around all the thing, your achievements in the field and like pushing the boundaries of our early chance of theoretical. But we are also saying, much the spirit of Galileo Galilei, and rather than die, I would say that's why I work like challenge stability of the time, and I think it is a spirit or behavior you should see like an example for, because we are living now in our time. They are different from Galileo. The science is not that like long. I mean, you feel that I look at me and so on. And now science is a collective effort, much more at the time. And that I think because then times and terms of challenges. But I think with the growing reaction of Galileo, very like back having like put lot of science for truth, for scientific method, and share that common privilege of being scientists trying to push the boundaries of our knowledge. So having said that, I really would like to let's say thank Galileo Galilei Institute, National Institute for Nuclear Physics. Also, was you system at Vietnam. Venuti there to take care of because you are, you start with tradition, it's like where you want, and I like the Eastern terrain of like frontier that we are very traditional of us places, and then Galileo I can't kiss here. So thank you very much with that. I have to do that. I don't know, it might have fan and then I was trying to stay in much on close. Thank you.
Thank you very much. Now I will call Professor Sonia Zirabinovici. He's a medical professor as well as of physics at the Hebrew University in Jerusalem, and the chair of the selection committee for the World Wide Web to be of the Galileo Galilei made together as I said, you can say that's really one month and my question and messages. I'm like I'm really like that should be easier. Yeah. And introducing them better versions. Please.
Thank you very much. Thank you very much. Dear Laura, Swiss Lance Dixon, and David Kosover, dear Director of AGI, Stefania De Cortes, President of the IFN, Antonio Giacomi, somewhere where Josule, and in the area of our party, following Rector of Florence University. Dear and friends, it is a special pleasure to be here on behalf of the members of the jury at the GGI at the event celebrating the outstanding contributions I will repeat the main six. This time, the Galileo Galilei Galilei 2023 is awarded to three non-sticks and then Kosovo for the development of powerful methods for high-order perturbation calculations in quantum field theory. I will say some closing words and then lay the short part of the document that Julie has prepared as a background for explaining why the award was given to these three scientists. So the award we stand up under the three recognizes human limitations and the relentless, yes they are, and the relentless and ingenious efforts to push the long arcs have shown a overwhelming number of power in taming the higher order of perturbation theory, described by the other things part of the scattering engines. The results of particle scattering are actually exact and reproducible. The perturbatives we use to calculate them is a human invention. It is a solar point invented to replace calculating the exact result of the scattering, which physicists are not able to do yet. This is a limitation that has to be accepted. In fact, even one would be able to calculate the exact results of the scattering, one could not confirm ever exactly. Another limitation we have built to the inability to measure anything exactly. Thus, there was celebrated a human effort to do the best and it is the best possible within limitations. It combines professional pride and ingenuity. I will add that those experiments to the end of the labor in the work could not be done without support of the technical and governments all over this planet. Here we are in the ages, crucial effort support to art and science was looked by the generator of crime responsible. In this context, I would make to recognize among the audience the presence of money, which achieved science, man, and geometric creators on all legend. I will now cite some lines from the background report the jury of the prizes presented. The past 30 years seen a revolution in our ability to calculate high-order liquidity perturbative corrections to scatter down doctrine in gauges. Today, a deep theory of perturbative scattering amplitudes allowed our calculation of collider processes with many problems in the final state and gravitational scattering processes at the multi-loop level. These results are needed for the parallel theory and experiment that adds Harshad from anywhere, and the estimation is requires to hit solid processes and searches scheduled hypotheses. A recent comparison of measured shorty-jet classifications QCD theory, including multi-jet sections, is a perfect more exams of that. Now, if I could have this slide. Okay, this is a comparison between this theory and Bellber's. The fact that you can different things that tell you how it says that the comparison is, and there's this same thing, the word of the people that we are the scientists we are recognized here today. So that's that we can read it differently around and tend to the lower around and translate with some subjects. The theory is also a weird continuation of the waves of black white everything with that precision, which will play an important role in the extraction of information from great waves of reservations. So many people have participated in these developments, but also have played the central role. They recognize the possibility of dramatic advances for introduction of novel excitement developed his insight into powerful analytical methods. The confirmation of Galileo has not moved away from the revelation and summation of individual finite diagrams, instead informed by a series of scattered longitudes based on more fundamental quantum theory principles. This is a development that was envisaged by Bernard and Stessler and is now globally realized. This is the same way that deeply connected three laws to Galileo Galilei is the theory to say psychology by generational thought. Anyway, and it comes from not now. And yes, it is time Galileo. Congratulations.
Of course, good. Congratulations. I tell you several times. Okay, so we can start with the first lecture by Professor Larson. He is professor what is Latin Europe and the Standard Minor and Security Center, the Stanford of the Stanford University, and the man that you actually academy. He was awarded subside prize of the American Society, and where he would get in 2014 and received the Humboldt Research Award in 2000 and International Spaces. And now the other prize that you have, Nelson, please, I leave you to stay.
Thank you, Stephanie, here. And thank you to the Missouri and those on does the honor under this award. I'm really out by this selection. Had academic time. I got to go now to see if I really believe like this. So much slam down around it was real. And I'm also just visible to be in the company of this wisdom says for their firewall more springs theory and the trajectory gravitational waves. And to me, it makes a housework or lived out in these days. In fact, I think the title I was talk, I didn't realize, or I wasn't thinking that Gil also says in the house around the and I've come to the notion that scattering out me to a like jewel, it's a very hard matter. And this talk, I want to tell you a little bit about our road discoveries and David and Steve, flesh that out in their territories. So how I want to point out is that the range is these scattering is you range from the large acrowider to laser. So that when you synchronize the experimental results, ultra is with theory come from event looking like methods that are happen on scale levels full of here. Everything way in spotlights and Zvi will tell us about the applications to that in his tests are. So I was already very important recently how they need to advance the reality of fits and they have to be having a chance to look at some of the rares in their direction. So now trying to gravitate it to a sort of help by Galileo. And this was the starry off which is where he first ordered on Jupiter and found out mentioned the telescope. And then I figured through all body got the most rough trouble with this center there. Led to this fine line for a while. It was not only the modern island, but I thought method something. But he was also source for Earth's physicist. And another very important aspect, this to seem a long 100 years later, was Yeah. Was Superman Chisilikar, and he had a quote that I wrote about black holes' nature of the most macroscopic objects there are in the universe, because the only LEOs in their structure are outside of space time, and for a long time, black holes were mostly visible. Now they've been visualized both through very large light microwave radiations and also gravitational wave. But I like to think of scattering to microscopic counterpart of the black holes that the was referring to. And in some ways, they're the most perfect microscopic objects there are in the universe. So they're not very illegal mathematical objects, but they also make contact directly experiment. In fact, that's the places the road one wheel theory direct contact experiment. In particularly amplitudes of a particular theory called quantum thermodynamics dominate the electromagnetic and the LEC. And we've seen that these amplitudes are very nice, very beautiful properties, and the one they have very kind of smooth behavior, which we use to calculate it. But also they have very many symmetries and sort of original representation, which are reminiscent of the rotational symmetries of jewels or like Plate-Telexol or something. And again, there are graphical versions, and we will discuss why black exists. That is, it is very large, as well as it is very small. So these days, the heart of our physics is explored experimentally at a telescope, a modern telescope, which leads into map hour. This is the large right-hand one. It's 26 kilometers around circumference, and it made the particles that can't be made where our particular Higgs boson was discovered there. And this is a judge, and at the time we were just getting started, there was also the system of the United States, which was canceling a little after that, 90s. This project, the LAU motivation for Sri Amy to start studying these deep level scattering altitudes back in the 1990s. And it's been a long, terrific journey since then. So the idea is that our lighter, it made an incredible number of revisions every second, and many of these are regular and had very different proper processes. And for example, discovery of Higgs bosons, you get final stones like places which contain 2 photons coming out and a number of muons, as well as very high jet acceleration. And others many jets when either direct regular the decay of the heaviest skills particle, the top work. And since it was our challenge on the 990s to fight out with elder way to contribute the properties of these molecules more additive or persistent. And if the water really are in the interactions of particles called gluons, which are not only your cousins of the photons, whereas the photons doesn't have an accelerator like this gluon does, and that may be a little more integrated lately. And there's an image of a artist's conception of an OHC collision, which shows the various aspects going on. And essentially, the outer part of the collision is very hard to predict precisely or evaluate. So it has modeled And that is both the structure of the photons closing in and the formation of jets highlighter to hadrogens coming out. So the part where to really make systematic progress on is this inner part of our vision, which we call the Orchestras process section. And then that is calculatable, at least extensible, thanks to asymptotic freedom. The note that the up-leveling gets quite small, really small, at short distance, which was found by Galileo Galilei and Pulitzer 50 years ago this year. So that enables the systematic computation in a series, the construct of human mobilization that Elio's suggestion, and before we start the race processes in the LA or have hadronite only coming to leading motor in the perturbation series, and now just 50 to 100 uncertainty is used in every series. And as a result of developments, not only us, but many other people who are also supporting these things very area. The NIL corrected now available for very wide energy losses, and even the automated led by Fabio Maltoni. And that was down the uncertainty, maybe 20%, depending on your process. And since then, you others are now into the next executive order in the series, and a very select number of processes are known to MNN-LO. And it's really remarkable. Of course, there is process that entire community has working. This is essentially the same picture that Elio's long, but it's an incredible feat in the experimental side to measure rates, orders of magnitude, and how free. Now, so it's not observable beyond the order. They're really a lot from all short this processors. And since we developed all this to compute these, then we have another machine to produce these short distance processors. And as we heard Elio's, there were many other approaches doing this calculation. We go back, that is Richard Feynman, who I was fortunate enough to have as a professor for some of my core sources. And he told us exactly what to do with later for the rules for QCD. He said, just draw all the Feynman diagrams. So a good draw wasn't one. And then you need to draw 56,000 others. And then you just have to add all up. Now, in some cases, this is actually what the best of us go. You can imagine that there might be lots of adaptations that happen. And in particular, for QCD, they make use of a lot of the massive nature. Feynman diagrams are just not optimized for these kinds of processes, and they're much more efficient assets. And just to say at the time we got started, there was some nice simple formula work for that 2 level for what we call tree diagrams. But this next order, it required these loops, momentum that had the integrate driver, and that was sort of challenge you got started. So in the early 1990s and maybe the late 80s, before I tried line though, this day that we're developing the methodologies sphere, which had all I want to black package. And by taking a limit, they were going to come out of rules that were successfully used by them due to the simplest was the tube-based into process as the tubes are one loop in terms of holistically amplitudes, which was a non-loop at the loop level at the time. Then I joined, and we pushed around on in the strict phase after 1 hour late. So this was the first phase to 3 amplitudes. And it had no recording complexity to it, and the 2 goes to 2. And it was just complicated enough, simple enough that we can make it relatively short. And complicated, and then we can kind of understand what was there, what wasn't there. And then these objects here are called the stationary area, and these spinner products were already used extensively at the level, and then we were able to add at the level. But what we can see the structure of this formula and the exact meanings of the terms are not that important. We could understand why these denominators are there, and that had to do with particular releases were on outcome coming here each other. And further, or more than they stated, we could see that there is a particular dramatic variance that appeared like 3 and 5 I1. But the other one you might have saw there were 2, 3, 4, 4, 5, all well with SSC. And so we think about that a little bit and try to understand what was there and what was there. And in this case, as I would even further back at 1960s, where the strong reference has had the bond John fine animals, but there was also strength for use analyticity to reconstructing the amplitude. This held a lot of others for us. It was developed in many different papers for the 1960s, different ranging thing led out to major string theory, like Galileo Galilei, Miguel Gustavo, Shapiro, and then kind of undoubtedly analyticity fell out a lot for the 1970s. Once there was a lot of the QCD and mind was able to be used. And our task was to resurrect for computing amplitude to perturbator QCD as an alternative to find the backgrounds. And so we go to the unitary at that. And the idea was, it seems pretty hard in the original Galileo non-lately, but with perturbation expansions, it made it much simpler. And we can use this to do some information and here. In particular, we could draw that represents the rescatter area of a particle, and we can find things its terms were 0 to understand why. These ones I was saying that when they were here, they had 2 laws of us sitting on them on, and could be distinguished with the ones with a minus 1 and a plus 1, which we were on 0. So we could see the patterns, and we could go from the patterns that we saw to turning it into a compositional tool. By work this out, then work out applications for the full amplitude. That was sort of the beginning of this unitary method. So we have in the amplitude community, I think, which is that it get a little lower computation power. In this case, it's the string-based estimate that's me and David did all the results. And the important thing was then look at the results. I'll try to understand their analytical counters, leading me to new relations. And then in terms of the relations around it, yet more power are things. Of course, we're also certain things about outer properties are also direct directories besides us not original. So this is sometimes available to virtuous circle. These I think John Joseph Saraswat have given it that name. And so it's basically as long as the previous is fly it. So another was that when you don't have enough how much QCC, try as there's a dozen of it available as for triangle, which is simple enough that you can push further. And with Wave Name Boundar, we did that, and we were able to just using what single evaluation for compute an infinite set of albinos in this area, and those others are called the only level of Mark Taylor to us, and they could have all be structured out of a very full set of inequities, which are shown over here. So the later red part earlier was around my subset form by my particular, this one by wild bar through. And in the NES4 area, well, I get the same name back there. Never mind exactly how it says is multiple set of one loop interconnects will be evaluated exact. So that was sort of the first hurdle route, unitary method. But I don't realize sort of the general principle in there. Many specific calculation, which was the notion that the amplitude sort of underload always change. They're like the Feynman diagrams are like lines of sand. And if there's always a column, you kind of identify them and see what they do. But then they be like good. And you should not even think about diagrams anymore. But you should think about amplitudes or more statistically. And what happens is you change these after and there's a way of doing that, like deform or the external momentum, which allows us to the tree to fall apart into simpler trees. And if this animation goes, there we go. It undergoes mitosis some sense and splits into simpler things. And that leads you a direct rate view, a set of recursion issues. Let's build the amplitude out of something simpler. Namely, you have more quantitative areas, separate areas, simpler. This was actually developed free level a little later here than we were doing some sort of things at the liquid level. But in the liquid phases, we were moving around in the space momentum instead of the after momentum. And so we'll think of things analogously, but by deforming the momentum going out of the loop. So here's your example of how you put two particles on shell, and there was this general linearity where you could put 3 or 4 particles on the shell. So those were early days, and though we weren't the first people to do this. This while here invented the triple cut, which starts the issue with blade shaver, which how the third blade lays this smooth manly on it. But I also realized that so he just in that shelf elements is where first running your hearing by I'll Thanks, yeah, Judge Justice. Yeah, So as a result of this method, there was sort of an explosion in the ability to do more and more complicated calculations at the LAC. So up until this point, around 2000, we believe that when the first 2 goes to 3 computations to our turn, and it took about a year to add one leg. But then it's basically about 5 years, a lot of large processes were done. We specialize mostly on vector analysis subject, but others like I've got it and Fabio Maltoni, you were doing AAC at LO, and then again, and as an ad LO, and there were other one where we're more specialized or adapted out of a large derivative process. And so as a result of that, many more processes became available. I want to point out our letters circa 2010, and when we all got a little bit different from we do now. But several little professors like Amanda Dobris was down there and currently at PSI in Switzerland, and also the dad there and work over on Young Weisleister. So that was a key part of our direction earlier today. We also had other contributors as well. And there already were people. This was a little busy. We were working in this area 2014, including Justice Awatana. I don't know who else also getting. But it was a rapid growing field. The many different contributions. So just kind of quick things by mentioning first that this area it started on trying to write more precision for the for QCD has really been out into many different areas, including not just QCD, but string theory, gravity, we'll hear this week, SMEM, which is studying reentrant corrections. And it also has been out many other areas in mathematics. And this was some of the times I think didn't use your amplitudes Copenhagen. And that I learned right glad about those continuous students around Robin about that. And the area is a little more recently or I don't know about mathematics. There's one of these the I just want to follow along briefly, which is anything for creative, which we discussed earlier. These are close and other UCD, but much less simpler, especially in the system of a larger colors we call it planar. You could call it I now have relative scatter outering. You can see the things there. You just can't see these UCD cases. They're too complicated. Recently, we were able to meet orders of this interpretive expansion in film processes where you're only getting about to lose. In order to rely on things being divided or we're cutting out the output into pieces. And in the end, that's allocated more and more holistically. But we've been able to do this in many pieces. And we have kind of going on use interpretive approximation and just using that in the couplet. And in fact, not in certain limits, it's an all already that. And but the dreamers just assess the information from many different limits and get an exact computable description, scatter out at least theory to all others there is some code. And we have in place where we can connect the things we're doing with perturbator calculations with the for others. I'll just here visit this and mention that in this the simplest processes are still really grand complex combinations following algorithms, and we have been changing by using an object cost symbol. So I understood that the rest was that is by Galileo, which was presented as translated as editory straight protocol is written in mathematical self-symbol. We can get results up to 8 loops in some cases, and this behavior is very distinct patterns, which I don't have time to go into, and I'll skip through this as well for a lot of time. So it says grow and it has many things to many different intervals now. Some people stimulate the and that can help me out in this internet construct called the polytype. Some people focus on the coffee, and of course, runs these tunes you must. Some people know it's measured in experiments, which is also free. Some people it is free of various. Anyway, it's growing and it become a very real. And this is that'll recognize that added us this with any single goal cheese. So thank you again to present our interactive committee. Thank you to the U.S. taxpayers who supported the audio my entire area. Thank you to my advisor. And my father particularly was he was an engineer, but he was a scientist who was osmosis. And there's another economic Galileo, which is that he looked on the spacecraft to go to Jupiter. And we have to go over to launch. And there's just pictures of the Galileo and satellite when the first Earth went up close, those Earths. So I want to thank him and just a few other people I had my way. I went back to high school math teacher. Another estimate is Peter going to help talk that. And my PhD advisor, I have Firebar, as well as my mentors at Slack, Shiftel and Michael Pestis. So, and I can't stop, of course, without to thank my mentors on our 30 years, Svi and Dave Davis. So thank you so much.
Thank you. As like this something. I don't know. It's in this music when I now that place or compound shows up with whatever. I like how to put it for. Sorry, please. So there is some one on what was something there. Some students. No, wow. No, what else? Scared. Maybe a little. Okay. So we will move to that. There is a David Crossover. He is a researcher at the institute. Yeah.
As to the two Indo-Europe.
No. We something, no? I started really and this geschichte university. Yeah, we are doctors of the nursery, feminine, absolutely the laboratory answers. His research has just supported the over the years that I now too. And I search research, and this special years. So thank you very much. Congratulations again.
Thank you. And I like to start by thanking Stefania Curtis, representatives of the GGI, Antonio Zonelli, representatives INFN, and also Elvage representing the selection committee for the honor being chosen to represent the Abbey Abbott's community in this award. And indeed, I do think of it as representing the entire hierarchy, many branches and many leads. And I have an annual in Montfrancing, 200 participants now, how many younger physicists. Fine, I am a future road, future successes. So the fielding of quantum and gathering atom into its essential object. What does that math mean? Focus specific quantities. We turn unsizable into usable. We use simpler physical quantities to determine how did one and go understand the like structure. We can use some example of that. Then we use that to stay standing. Even harder calculations. Then we repeat. That's my version of JJ virtuous search has been playing out now over the last 30 years. So our new social motivation study Jack and Jack and sure is well known on his whole particle physicists. But that's you already would put it at on the light letter and it does increase emphasis. Yes, and it does. So this event had a 9 pleasure. This first morning season at a start focus with some new at a thought that you really the events in. But by the time definition should and as other period today should read there was less. So in perturbative GCD, the coupling we got so fancy. And it also that's that leading order, interpreted extensions, and early doing you quantum description. Here the subject, but it's not duty. We only really like the next one order, which you use in one book. But here's first for that Jack quantum community. I was Matt at the time. Or if I had got to go with my destiny dream. And the on top about going vision in the order. Very test. Today they really are with help from the many able to mitigate of being in the UN. So they're here. 2 ingredients you need most different. The focus on it. One way so-called universal resurrections. My theory we're not particle to see that the distribution constitutions where the aiming the sticks how and I wanted to look a little bit back at the of scattering out and first, there's the European fine line and hard-time model, late 60s, the really first the DD and so we've done the kind of field theory and have the version of theory of a slang reaction more form on the dynamic. Now, the 1960s, mostly, and then the Dark Georges who wanted to do it. But three no RTs, there were a lot of people pursuing some modern thing from research theory. People were interested in the analytical behavior scattered around. And he ideas of strange being, sounds theory, or everything by looking at the properties. And also, when the going got tough, the kind of cheaters really look to find violence. Our task is to take this idea much more seriously. And the other thing that has become kind of standard and very nominal in the late British, I would like just give credit for the 18 trees out in India, also if the name is VT. Now, there were many different ways of implementing them in gauge efficiencies and Haiti, and the one that then maybe the most luxuriating and the most so-called Chinese magic that and it's a very interesting paper because this is really one of the first impact based on the amount how the Mao Dai is Chinese slowly. Today again there's in spite of everything very hard China the very bad wisely and after honest people accuse using sense that people deserves credit has started. And of course there's a celebrating Taylor ladies is built that out of these things she's cutting a very area and was laboriously how chapterly true experience point for Hiller and realize the generalization. In fact, this person can warm. What's let us down now? No, I'm just my bar shoe. But so they have they don't bite in my bed credit to this particular four horns inside the way it's sitting this. So the Tory grow milk tea started from the other on CC, and I finished my degree Howard Jolly Giant CDE effective, and then I arrived at just as Columbia all lifted high with they and then I kind of did nothing not productive. My man and that's when I it. It's making right and January he said just and work on this the problem new way to be out. And this is something that's we had in mind a lot of this position, but this was calculating by 5 hours. It's a more feminine doing something that even an English solution. And not Miami and low. So the one thing that the paper, of course, carried in was that my thesis advisors know him and would excommunicate me from the people consider they're talking to. And like anything, I don't actually really about one extremely reasonable guy. It's best that it's legally he understood for Hitler to be just correlated with competent objective space. And it turned out to be one of the seeds that Whitman later built those. And clearly everyone knew it was an important paper, and no one really knew how to generalize. And in fact, then it took Edward Whitney 15 years to figure out how to do that. Shows it was probably so we wanted to go on and do one amplitudes, and so to the late 1980s, the state of the art was the four-line amplitude calculation by Elliott and Jim Shinks. And those are the notes that even masters hard or divorce calculation. It was many, many nights, maybe even a couple of years of hard calculating. I've never actually been sexting. I know through his CV that he's probably burned it out analytic calculations, went off to do lattice calculations and more numerical things here. Today, it's the kind of calculation that I passed all the techniques that have developed as something you can graduate in days. And in fact, the very, very bulk of good graduates should probably do in a few hours. So Tzvi and I started by applying kind of a lot of string theory and generalizing the work that I'd learned from power mesh background. And it was down to a simple set of rules. And in all fairness, we probably took longer to do it this way than nominally the original calculation. And that, of course, is not too convincing to. So we were, of course, using inducers, spinnericity, as everyone basically has some span. We were, for this, saying a desert. And the lead protection traverses that desert. And that protection, fortunately, came in the first source of alveolar, who was then and is now a leading figure here, perturbator of the quantum dynamics. And he's not at all the kind of person who would have. All right. About I don't know. No, I'm not really. And then touching it, and then that is that boat. Think of. And so I said, "I died of women." Okay. And she was not at all the kind of person who would have followed the kinds of calculations that we were doing, very different style. That was also very, very in my mind, that was really critical to us in those days. We also started slowly to attract some attention from more senior leader in conservative QCT, in particular from Zoltan Kuntz, who was at the ETH now American and both encouraging friendly at it. So okay. So Lamb had a showing down there because she shoot 5 and this was the first really was us. And that was something that must be kind of understood an answer that there was really something here, something to look at. Yes, even no one else really appreciates. Now, previously heard you check the calculation like check and cuts and track, but we didn't really read snazzy on that did more work. And Julie Dave realized this she ended up using heredity, explaining it's too I'm full CD. Flame voices in the sphere as your average numbers, maximum system symmetric, no security. And this great light routers were all gone. My other source making from continuously leave them that. So we say together. We have the fully efficient. And I got easily. We have this. They don't go short. Basically, there's multiplicative factors and 3-level is all. These are artists remember extends ones supplied by last the way it is. Fine just. Again, this is something that you can do in an introduction, not like a just it's almost back an envelope exercise. So the fact that took serious researchers a while to do something. It's just pretty. I actually think about it as the science grade progress. People can now go complicated and on the base something then this is complicated and has been made expressions. Anyway, so then he had a new fuel and he starts scouting out to there. So of course this thing that didn't get it. Look to come to I lines goes so it's far harder. And most scholars use you let's say Z or WU. Let's choose jazz after highlighter for jazz. Right? And I was and yes, the time I worked for it. I mean, was this here on Ways. Also, it's even manufacturing very first drastic in the 2 and I had to do they didn't realize, but it was even really still seeing one of many how common in the sub-level and remain the active researcher and define mine. So that's that. The other thing that second is the idea of having not just physical stuff, just to either but having anything. In this case, a triple threat. And that's when then actually I went to searcher wing and on that is the UV. So also to cut that and structure to something that an animator did is there correctly. It's not something that you learn and then general analysts by researchers who are saying them young people and can use to be here. So that was also the side. Started to track facts. Younger regular people at me. It's just bad stuff. The first test is also, I think, played a role in the later. So we continue these books. And so magmatic that's my theory. And I was this is by now lately the 2000s. And we about this. That's often computed to splitting amplitude, and then I realized a certain fan in the MES theory, the phenomenon out of you is like last square here on the moment. So at a KIT workshop, the Fergan and I with 2000 more I gave a lecture under Zen this work. At the time, David Edos was ready to be recognized by playing LNO as he is today. When the seminar was over, and the seminar was over, said, okay, so he's done from one room to so goal-wise. But to his credit, and new results over in becoming my changed my agree with. So the fact it was the start of a long, fruitful line of search which pursues my the lamb. They're not for some of those that line of search from lamb as basically showing the enormous at very high land. Actually, the very fact that n equals 4 SUSY is simple, so simple to do it in the unit narrative acid would have shocked anyone to mid-1980s because you added all these leads, a part of all these leads strain coming free, so the symmetry, people would have had exactly the opposite of ceiling. This was by far the most complicated theory down instead of this. And that's again, our we're dual food and made names use look complicated, very sensible. They have past solution. So the other thing, and never really know exact eyes. I gave a talk about this at Institute for Advanced Study in front of like talk, and maybe you've been thinking about some of these beforehand, but this certainly help push a little interest in twin interest. That's a slightly different behind any restricts or those no ordinary web. And that faded ornament now size. But these things that I would say for the most of during not challenged first of all the broad field and then were then stars. About to wrap out the stars. Some of them are now senior researchers at UCLA's Bay. And there were other political 40 years time. I am Peter Search actually. He decided there's better there is a lot of line masons and sour on. No one's north. The other thing that it's brought to us are the Rizzo who has with and they think that Terranarian they take factization even simpler. And it really our sure fact I am not just essence in the large varieties of the functions that arise in scattering iron tubes. And that in turn was triggered an enormous amount of flying lime down. And the iron mentioned that in some sense the tree level finding in the principle that was a key calculation machine many years after the finding of the principle loop element. History doesn't always work. So, of course, then we wanted flight lines to see lighter, and so with a few hard work of the enthusiasts and collaborators went on to completely all applets and made them. This was 12 hours later. Henny and these pieces essentially already done in 1990s. Sure, and there is the completed in 2005 and 2006, and combining territory the WMU containing sure. And I was in a flash lasers, just one of them, and this is the result of which sure. So not. It's your doing these series high characterization not simple enough. Highlight and but on it there's like button. There's a harm that follows those years was problem and that are thrilling on gives you at page 8 is only a definition. So though this is not a way that we're going to be and suit every other day and so you compare with stupid. So instead start about human then there and it's the whole calculate this recent mariner, so for the mariner, really to nothing in there, it be these. Motivation is like learned to what the high sign will call the NLNL, which the mark part, a word derived by a lot of other people. Well, and whom not likely to choose. And so more the Naglat has collaboration in younger sizes and as a that is them marking transition to a number of already Steve with the archive says we're now the other thing that just sound I'll say that the eighth paper is that there's little connections. So look at methodology well not unless we're security then part of our work. But that is initially paper. Active paper is done astound out all really high. Both the what not to the penny down inside sign. Can you maybe if I tell down to the crowns this slide? Campaign. So let's do that just like so if it as I say the carnivore words carried down the hill, to do the MVR. Let's go to the magnetic. So Zoom started running things WM was 3 gens, and as this is here using here so behind I am maybe MVR data. Of course, the 4 there was really you see that so there where and as the sure looking more looking at say gent spectroscopy. was really uncertainty that add order and how more qualitative fiction researching quantitative instruction they reduce and fantasy resets at certainty at net order go to the maintenance. We continued on also we scored jet and you're in CC the battery or jet number and it's very good, but in LO we have not precision physics but quantity that's by with me the help they find this and steps out was there and we then went on this 5 judge and at this point we had an data and parameter here a role and so there's energy but even as you drop them out of ways to W fixed never English back and then after those sheets check and on read other. So this is a version of the timeline line fourth words and comes up on the hypothesis again when remember however our estimated is a CHP is acid right but so decade out one leg turns to the recognize or sesame the earlier they should be their leaders here and telling how England and then other Italian colonies and then with these American were new people very great big meat had more judge and had more really neat team flowing and a bespoke calculation of processes to an industrialization and of course like Fabio and Tim head editors ready to automate this smart or re so no tools on sure to kill you and you but so the frontier today that so the blue cars for doing the mechanistic order or like first vision order and I know more sports count I ride movies more particularly loaded is to recreation to go say about half hawks subject either about balance to the recreation with the late lane mind is making so something until you see one looms of each solve all the fun of something and do by direct integration and they're then progress mirror truck the analog line in the parity construction and as there are many ideas that like rational structure young Talcott sisters the audio idea is outside she those ideas and there is a appreciation of not appreciation to geometry running in import or first negotiation. So the amplifiers reveal the model of course the connection is and there's a connection to matting us and money on the end on the great on the obviously ideas about new ways of looking on a steel field used to thinking on a steel field by how it makes the on it doesn't just deny it either for different purposes different facets on a field theory us and that action discovering and I'm trying to find ways of thinking about what ways to feel that I believe he to I wire here it's trying to light them with direction. There's connection the distress period connections ability plays in Fort World the study on the maximum sees symmetric any forward words as no super private eye you'll share maybe a little bit about that from Baby and Superior very important rivalry orientation and of course that connection LA phenomenology these to now out he used in Harrison sunshine live lamb Of course, we're still going to an connection in 60 start time. And one relatively new connection is that to grab patterns will down on these species. And it's a very fortune that, in a sense, allows us to walk footsteps at the 2021 one. So now, having to consider to gravitational waves. On the side of application talk, maybe you may give it business. And not even the application is not fast and I have a flag, but my very Chibo Damor did printings earlier and he's telling to amplitude text for using not an these to a certain to the scattering iron which will have connecting issues show you more detail to the effective on body. I only in English. These you find I have this carrying on my front justice America shared out that is your. So that I think begs the differences and maybe more roundabout way. Also, in terms of this work we're doing, there's dealt with a lot and run and a bunch of then graduates see now. And now I was talking to fellows. I wasn't sure when the audio hadn't see theater to how well represented our collaboration. So the idea is that you want to find massive observables from Monty scattering and music. And it's not a very enjoyable and if we're making clarifying at least how now you can do this. And the idea is you're still looking not at the mountain states, Onions, just scattering out around. We pick here some well-defined irons, theory, the spots last 8 weeks, and then we use breastplate and scattering thing. Puzzle over this a long line. Figure out, so very satisfied. Do that, then you take to the bus, machine, store authority. Up, you realize what rating wave meters or the photons of the gravitized. And when you're taking in observable, the singular terms will count. So it turns out to be nice in a historical and spinorial world express the waveform in the terms of Newman and the scalars, and this has to be the one that's relevant. Gravity. And this is actually in all orders form where you look at specific orders in perturbation theory. You see the double copy structure, very direct rate, also something which expand on. And one of the things you learn was that if you're looking at the wave rate scatter out events, it's essentially the light. Turning into questions of calculating that a certain radiation kernel. For those of you worried about the H-bar in front, there's actually still the secret H-bar, one of H-bar squared that's hiding the two inside the amplitude. Canceling with. And when you take this radiation kernel and do a sort of phase-based integral, then you get the wave. So we're in the start of a journey, and it's really been fun to take these first steps in a new invention. I'd like to close by, of course, thanking my fellow collaborators and trekkers, and this image, maybe how they see themselves today, how I saw it at the time, and of course, a very long list of collaborators here over the years, a few of whom are sitting in the audience. I'd also like to thank funding agencies that have supported my research, my collaborators' research over the years, particularly the European Research Council, which has played an important role both in Black Hat and today in my gravitational sensors. And finally, not the last, but least, I'd like to thank my parents, who were storytelling themselves, providing a very rich intellectual and scientific environment at the dinner table at home And that's one of the new things that how to be in today. Thank you.
Thank you very much. I just stopped all because I really need a break. Okay, we will have a break for last the lectures, and if Banana does just is here. Because I cannot organize the director villa of the villa, but if you have curiosity, you want to know something about place, about the Galileo here. This is Madame Rosa, she's there. She's an art historian and contemporary art, mainly works in the field of valorization of cultural and historic scientific heritage in museums and archives. And she's currently a research fellow at the GGI because we are co-curating a cultural project taking place at the Villa Galileo for the dissemination of scientific research through the languages of contemporary art. So if you have any curiosity, please contact her. We have a break of, half an hour, and then we reconvene here. Thank you very much.
Please have a seat. Okay. So it's my pleasure to introduce Zvi Bern, professor and director of the I don't know how to pronounce. Baumik. Who is here. Thank you for being here. Institute for Theoretical Physics at the University of California in Los Angeles. He is a founder, with his co-recipients, of the modern field of scattering amplitudes in quantum field theories. He contributed to various topics, including supergravity, supersymmetric gauge theory, physics at the Large Hadron Collider, and most recently to gravitational wave physics. So it's my pleasure to have it.
Well, thank you.
Please.
Well, first, I'd like to thank the committee, the GGI and the INFN for this fantastic honor. And I have to say I'm truly humbled by the idea that we won a prize named after Galileo, and also because of the spectacular previous winners. So today I'll be talking about scattering amplitudes for gravity. And first, I'm, of course, absolutely delighted that I won to get the prize together with my good friends Lance Dixon and David Kossauer. We have 43 papers published, all three of us, and many more papers in pairs. And David and Lance, they've already explained the history of scattering amplitudes, the basic concepts, the on-shell methods, the unitarity, various bootstraps, and applications, collider physics, QCD, supersymmetric gauge theory, and also gravity. Here I'm going to focus more on gravity, and first the on-shell amplitudes way to be thinking about problems in gravity. And I'll show you two examples where we've applied the techniques that you heard about to supergravity and ultraviolet divergences in them to understand basic issues about the theory, the non-normalizability of the theories. And also I'll explain about gravitational waves. So back in 1993, I dug up these photographs. There were only 4 believers in amplitudes. And a lot of the belief came from this formula that you already saw in the previous talks, this Park-Taylor formula. And in those days, there were very few people who understood the significance of this formula. In fact, the people who wrote down these formulas, they went on to do other things because the path wasn't so clear. And there were various issues with this formula to apply it to collider physics to actually do physical predictions. So, and there were exactly 4 of us around 1993. There's Dave Dunbar, who at the time he was at UCLA. And these meetings, well, there were only 4, so the 4 of us would fit in the broom closet if we needed to have a meeting. There weren't very many of us. And since then, of course, the field has blossomed in many directions, as you heard in the previous talks. And there's quite a few. It started right here in QCD, branched out to many different areas. I'll talk about supergravity and gravitational waves. So the basic tool that you heard about, that was explained in some detail in Lance's and David's talks, is this idea of unitarity, that if we want to build a more complicated amplitude at higher orders in perturbation theory, these loop amplitudes, the way we do it is not by starting with Feynman diagrams, but you start with on-shell tree amplitudes, lower orders in perturbation theory, and systematically build up the higher loop contributions using this method. And of course, here I won't explain exactly how this works, but it basically you assemble information from these different generalized unitarity cuts. And this, as you heard, was used for this next leading order revolution in QCD collider physics. And what I will do in this talk is talk about applying these ideas to the case of gravity. So normally when you start with gravity, the way you do it is you look towards Einstein, you look at Einstein's equation, you start thinking about geometry. And that is not the way we work. We start someplace else. We don't use Einstein's equation. We don't think about geometry. We're interested in perturbation theory, and our starting point is this concept. Gravitons are massless spin-2 particles, and this was understood by Feynman, that you could build up Einstein's theory of general relativity order by order in perturbation theory starting from here. And this is in fact a Feynman diagram written down by Feynman. This is for quantum electrodynamics, but you could do exactly the same for gravity. The only difference, instead of a spin 1 massless particle carrying the force, there's a spin 2 massless particle, but everything else is the same. So the way we are going to think about gravity is the same way we think about gauge theory. Okay. And just to be clear, this is not suited for all problems. Problems where the geometry is very helpful, this is probably not the way you want to do it because you lose the geometry. It's suited for perturbation theory, and also where you have asymptotically flat space-times, then it's especially good. And one of the problems where that's true would be the problem of classical gravitational radiation. Okay, so what goes wrong with perturbation theory and gravity? So we can think about Feynman rules starting from the Einstein-Hilbert-Lagrangian. And the way you do it is you take the metric and you expand it around your favorite background, maybe flat space, or it could be some other kind of background, a geometric background. And then there's fluctuations, which are the graviton field. And when you insert these, this perturbative expansion in this, there's a coupling constant here, you insert it into the Einstein-Hilbert-Lagrangian, and you generate Feynman rules. Very quickly you discover something very unhappy, that there's an infinite number of interactions. And in fact, it looks much more complicated than the Yang-Mills Lagrangian on which QCD is based. But in fact, if you look at the details, in fact, the theory of gravity looks much more complicated than gauge theory. If we look at the interaction of 3 gluons in quantum chromodynamics, then we have an interaction vertex in terms of these are momenta, and this is called a color factor. It's just a matrix. If you compare this interaction vertex for 3 gluons to the interaction of 3 gravitons, you see very quickly that the gravitons are quite unhappy, in a sense they're quite complicated. In this formula, you see a P6, that means 6 permutations, so there's actually 6 terms. See the sim there, you're supposed to symmetrize in the indices here. Gravitons are symmetric tensor, and you wind up with about 100 terms, and pretty soon you conclude that gravity must be a nasty mess. The gravitational perturbation theory through Feynman diagrams looks very, very complicated. But in fact, if you've listened to David and Lance's talk, you know that we should be thinking about this problem the on-shell way. We should use the Einstein relation between energy and momentum. If you do that, you discover something very interesting, which this has been known for quite a long time, but the significance is more recent. In the on-shell way, you find that the Einstein a 3-graviton interaction collapses to look like a product of 2 gauge theory interactions, 2 Yang-Mills interactions. The Yang-Mills is just the name for the gauge theory. And it looks like a square. We call it the double copy. There's 2 copies of this gauge theory interaction. And what you learn is that, in fact, there's very simple interactions in gravity dictated by the fact that gravitons are massless spin 2 particles. This interaction is dictated by the fact that the gluons are spin 1 particles, massless spin 1 particles. And I guess you can see spin 2 is like twice. There's 2 copies there of the spin 1. Now you might say, okay, that's very amusing, just an accident. But in fact, from 1985, we had a very good idea that that was not an accident. There was something deeper here. There's a paper from Kawai, Llewellyn, and Tai coming from string theory where they looked at the low energy limit of tree-level graviton amplitudes, and they were able to express it in terms of these gauge theory amplitudes. It was phrased in terms of closed strings and open strings, but when you go to the low energy limit in field theory, it was a relationship between gravity amplitude and a gauge theory amplitude. And in fact, you could do this for any number of legs, arbitrary number of legs. Sometime later, we wrote down an all-in form for that. And this is something very profound. It says the 2 theories are connected in a very deep way. If you look at the perturbation theory, first thing it says gravity is derivable from gauge theory. And the funny thing is, if you look to this day at the Lagrangians, this looks very mysterious. There's no simple way to understand this through looking at the Lagrangian of gravity and gauge theory. And to this day, there's really no hint for that. And the other thing that's very important is that it's generally applicable, that in fact, it's not just limited to particular string theories, but it's something very general that you can do in gravity. Now, it turns out that the secret for cleaning up the previous formula, it's not to be found by looking at gravity, it's to be found by looking at gauge theory. So let's look at gauge theory again. So here's the vertex, the 3 vertex. This is Donna-Abelian gauge theory. These color factors that you see here, they're basically matrices that connect different types of gluons based on a Lie algebra. Lie algebra is what they do for a living, is they satisfy the Jacobi identity. So these color factors have a Jacobi identity. And what you can try to do is identify in the kinematic part means with the momenta something similar. And in fact, at 4 poles, you have on-shell legs. It has to be on-shell. You won't see anything. It has to be on-shell. So these have to be physical gluons in the high energy limit. And you can do a little bit of a rearrangement that you take the Feynman diagrams. You can do this with Feynman diagrams. This 4-point interaction and you absorb pieces from here whose color factors look like these three. So this one just gets absorbed in the other ones using this great identity. 1 equals S over S, where S is 1 over S is the Feynman propagator. You make that rearrangement, and you can check that these kinematic numerators, these n's come from the algebra of the numerators. You can check that they satisfy the Jacobi identities. Now you'll say, okay, that's very amusing, but so what? But the so what is that the secret of perturbative gravity is hiding in here if you know where to look for it. So let's suppose you take an n-point tree amplitude, and what you do is you arrange it so that the color factors and kinematic numerators are arranged so that the same Jacobi identities are applied by both. Then something magical happens. If you want to go from gauge theory to gravity, you take a color factor and replace it with one of these kinematic numerators. As simple as that. And that's how you can now do tree level gravity. And this works for Einstein gravity. Now, this thing is, I'm sure, very profound, much more profound than we've understood so far, because you find the theory of gravity is based on these kinematic numerators, these n's, that are identical to what you find in gauge theory. So these two theories clearly belong together. Perhaps unified description of gravity in gauge theory, presumably along the lines of string theory. Of course, this type of argument can't be used to prove string theory is correct, but it's definitely very suggestive that there's something deeper here. And in fact, these ideas, I'll just say a few words about it. They actually extend to many theories which are not even gravitational. And what these links represent are the underlying theories which you use to build the double copy. These are the double copy theories. So you take two theories, you put them together. If you see a link, that means they share one of the copies. Okay, and there's a whole way of understanding different theories and how they link together of these scattering amplitudes. And I should add, for Lagrangians, you're not going to see anything like this. Okay, so the summary is, in a very precise sense, we can think of gravity as two copies of gauge theory, and specifically that the graviton is two copies of gluons. And by a precise sense, I mean that we can calculate with it. We can do calculations. And if we use the unitarity method combined with what I just told you about these tree level amplitudes, you can now systematically build up very high orders of perturbation theory. And the two examples that I'll say a little bit about here is first, multi-loop supergravity, and that can be used to understand non-renormalizability properties of these theories. There's lore that says all point-like supergravity theories or point-like field theories of gravity are non-renormalizable, and the question is, how do you know that's true? There's only one way to know that that is true. You have to calculate and find the non-renormalizability explicitly, otherwise you're not sure. And the other example is high order corrections to Newton's potential from general relativity used for gravitational waves. So the first example, let's look at the ultraviolet behavior of gravity, and you can compare gravity to gauge theory, and you encounter integrals in the Feynman diagrams, which look a little bit like this. There's some Feynman propagators, and then there's a vertex, an interaction vertex. In gauge theory, it's 1 power of momentum in the numerator. Here it's 2 powers. So if you look at these integrals, this one has a poor behavior in the ultraviolet. As p goes to infinity, this is poorly behaved. Okay, and that's the essential source of the statement that gravity theories are non-renormalizable and they must diverge. Okay, now you can immediately a problem, especially in the philosophy of how we think about things. We shouldn't be thinking about arguments based on individual Feynman diagrams because they are not gauge invariant, they're not physical. And you have to worry about cancellations between diagrams. So the question is, are there hidden cancellations that we don't know about? Now, the theories we're going to talk about are supergravity theories. N equals 8 supergravity is the one that should have the best behavior with the highest supersymmetry. Now, let's have a look at the question of in N equals 8 supergravity and other supergravities, where's the first ultraviolet divergence in 4 space-time dimensions? And over the years, people have made predictions based on power counting. It's more sophisticated versions of what I showed you with the single Feynman diagram, but you invoke supersymmetry. There's something called superspace that you use. You try to make some arguments. Actually, here we are. So back in 1998, we thought there would be a divergence at 5 loops based on some partial calculations we had done. That's what we thought. And over the years, there have been different versions. When we started, the accepted wisdom of where the divergence should be is 3 loops in N equals gravity. Okay, and then over the years, it changed based on once we started doing calculations, and people looked more carefully and came up with 3 arguments. But let's actually have a look at the the list. Yes, the list of the scorecard, so to speak. Scorecard. So we followed this basic principle. If you want to know the answer, you should just calculate. No arguments. You should just find out what the truth is. And you can see over the years, let's see, starting with we first did some 3-loop calculations. A scorecard, basically, if you open your mouth about this problem without having a calculation, generally you're wrong. Here's a counter example. In fact, there is in N equals 4 supergravity, so that has less supersymmetry. There is, in fact, a divergence. But if you look at the details, and we have the details because we did the calculation, the divergence is a little bit peculiar. It has an anomaly-like behavior. And if you're looking in a theory where that anomaly is not there, like N equals 5 supergravity or N equals 8 supergravity, the question still remains. Okay. And I should point out, so first, that track record is not great for predicting using symmetries. But the conventional wisdom is sooner or later it has to diverge, because you're fighting a very poor power. It has to do with the fact that Newton's constant is dimensionful. Every order of perturbation theory gets worse. So independent of the details, you still might believe that, in fact, the theory is going to diverge at some loop order, and that would be the conventional wisdom. Actually, I can show you here. This is 2 early papers. This is the very first paper. There's Lance, there's Dave Dunbar, and their 2 students. This is the very first one before we had the proper double copy. We were using the Kawhi-Llewellyn tie-way, and you see we already could see that we could exploit this double copy relation between gravity and Yang-Mills, and we also understood that it would have some information on, and this is the one where we thought, based on extrapolating what we saw, that there would be a divergence by 5 loops. Yeah. And then the paper where we got really serious and started really going after the conventional wisdom was this one. So this is with, there's David Kossauer and there's Lance. The Radu Roybon joined us, and there were 2 of my students who are both faculty now. There's John Joseph Carrasco and Henrik Johansson. And in this paper, we showed that the 3-loop divergences were not there in this theory. And that of course, generated some interest in the gravity community. Now, I'm just going to jump to a puzzle. So we've calculated pretty far now, And we don't have the answer. Finite theory of gravity, a finite field theory of gravity, but there's definitely a puzzle. And the puzzle is enhanced, we call it enhanced cancellations. The definition is if you look at individual diagrams, the individual diagrams necessarily have to have a worse UV ultraviolet behavior than the full amplitude. So individual diagrams have to be divergent, which you can prove through unitarity that it has that format for individual diagrams. But there's an extra cancellation, and the reason why this is interesting is because this cancellation is not of the standard type. It's not non-abelian gauge theories. They do not display these enhanced cancellations, and normal formulations of superspace, of duality symmetries, do not exist cancellations. So it's something beyond, say, the standard understanding of how these cancellations happen. Two prime examples: n equals 5 supergravity in d equals 4 at 4 loops. That has one of these cancellations. Another one is, it's called half maximal supergravity in 5 dimensions at 2 loops. And maybe just to explain a little bit about the cancellation, this is n equals 5 supergravity at 4 loops. It's not divergent. But in the double copy, you see it's built from one theory that's divergent times another theory. So it's actually something else is happening to make this thing finite. And there is actually a calculation which I hope we'll work on over the next couple of years, is the n equals 5 supergravity, 5 loops. This is a doable calculation, which is not the same as saying it's a simple calculation. Okay, so let's get on to gravitational. Of course, as everybody knows, the era of gravitational wave astronomy has begun. And what got me interested, as soon as I saw the paper, anyway, someone told me that it's in fact brighter. That event that was discovered was brighter in gravitational radiation than all the stars are in the visible universe in electromagnetic radiation. And that was really cool. So I said, I got to work on this stuff. But the problem is, how can we as particle theorists help out with the core emission of the gravity? So you have to find the right problem. Well, maybe before we do that, let's just let me just say a little bit. What do black holes have to do with particle physics? So there's particle physics. Particles come in and they go out. Unbounded trajectories. We use gauge theory, QCD, electroweak, quantum field theory. For a bound orbit of two black holes, we don't use quantum field theory in general because the black holes are big objects. We use general relativity, classical physics. But there's a simple insight from effective field theory ideas, and this has actually been known for a while. The black holes or neutron stars, they might as well be points if the radiation is long wavelength radiation, and the separation between the two objects is large. Then they're points, because that's definitely in our wheelhouse. And this was understood a while ago, and also it's very systematized by Goldberger and Rothstein as a way of thinking about the gravitational wave problem using field theory. And then just to lay out what the problem is, so you have two black holes. They're in orbit around each other. They're spiraling in. They're emitting gravitational waves. And in the beginning, they're far apart. And then in that place, you can use perturbation theory. Then at the merger, you can no longer use perturbation theory. You have to use other techniques. Numerical relativity will work here. And then there's another phase where you can use a different kind of perturbation theory, where the final black hole is just ringing, vibrating. Okay, and this is the part where we can work on, contribute to. So just a little bit of the history. There's post-Newtonian approximation is the way that this is traditionally done, and you expand in Newton's constant and the velocity. For closed orbits, nearly circular orbits, the velocity and the Newton's constant are equivalent. And in the center of mass frame, you can just write down a Hamiltonian. First term is Newton, second term, Einstein, Infeld, Hoffman, and then you can march down the orders. Over the years, people have been calculating higher and higher order. See, relatively recently, the fourth post-Newtonian order was done. And the reason people do this is, of course, because it's necessary. Oh, and about the future. So the future is in fact very bright. If these are the future detectors, so and if you look at where we are today, and this is a sensitivity, you see there's factors of 100. So that have to go much higher order in perturbation theory. In the post-Newtonian language, it's another 2 orders that you have to do. Okay, and the solution to this problem will come from many places, and of course we're working on contributing to that as well. So when we started working on this problem, we were faced with a simple puzzle. We said, okay, we want to work on this, and we have to find the right problem. And there's multiple problems you can look at. There's spin, finite size effects, new physics effects, radiation, higher orders in perturbation theory. So which problem do you want to solve first? Well, there are some constraints. It needed to be a difficult problem using standard methods. If it's not difficult, what do they need us for? So it needed to be non-trivial. It needed to be of direct importance to the theorists working on LIGO Virgo, and it needed to be in a form that can enter the pipeline. Well, the answer to the question of what's the right problem actually became very apparent, as I'll show you in just a minute. It's to go to higher orders of perturbation theory. First, we were naturally, this was in our wheelhouse, but more importantly, it was very clear from the literature. This is Thibaut Damour, Alessandro Bonanno, previous winners of the same prize. And David already mentioned this. There's a beautiful invitation. I've never seen anything like this. We urge the amplitudes experts, so they're talking to us, to do third post-Minkowski and effective one-body Hamiltonian. These post-Minkowski, what that refers to is you make an expansion in Newton's constant, but keep all orders in velocity. So it's related to post-Newtonian, but it's a little bit different. Okay, and then at the Amplitudes 2018, in case we didn't get the message, there was Alessandra Bonanno who came and she explained once again about the importance of doing these calculations. And it was definitely very hard to resist this problem because it was clear this is the right thing. The way we do it, there's a beautiful paper, Chung, Rothstein, Salon, that laid out how to combine these two. So it's effective field theory community is working in harmony with amplitudes community. On this side, we use all the ideas that I told you about. This uses the basic ideas of the effective field theory that I mentioned a few minutes ago. And you combine this in just the right way, which I don't have the time to explain, to extract two-body Hamiltonians, potentials, corrections to Newton's potential. Now, it looks a little roundabout because you start with the quantum theory, you take h bar, it goes to 0. So maybe that's roundabout. But on the other hand, we are very good at theory and gravity. So it seemed completely natural to give this a try and see how far we could go. And I should mention this way, this was the original way we did it. Now there's much more ways. There's, in David's talk, he mentioned their beautiful work on directly extracting observables from scattering amplitudes. And there's many other ways of doing it that are also much more direct. So this was our first calculation. It's a conservative third post-Minkowskian Hamiltonian. And this is the third order in Newton's constant, all orders in velocity. That makes it the post-Newtonian. And then it's these coefficients are the corrections to Newton's potential. Newton is hiding in here. It's very hard to recognize because this thing is valid to all Lorentz invariant. Okay, Newton didn't know about that. But Newton is in there, and Einstein, Infeld, and Hoffman are buried between these two terms, and then this is the next order, the third order. And there's this logarithm here, which actually played an interesting role in trying to understand this formula. Now, the question is, how do we know it's right? Now, that's, of course, a question we spent an awful lot of time on. We had some checks, original checks, where you could expand in velocity and you compare in the overlap to the literature, the post-Newtonian literature. And that worked, and there's another one. And then the best check actually comes from Thibaut Damour. Why his check was so good is he was very skeptical of our formula because it had to do with the high energy behavior, that logarithm I was referring to. There was some issue there. And in fact, he proposed various corrections to our formula based on trying to improve that high energy behavior. In fact, he was so eager on our formulas, he went off to do a difficult 6pn calculation, and it was a great delight. We didn't have to do anything except wait. And then they did the calculation, and they, in fact, our formula, and also confirmed by another group. And there were various other checks, including clarifying all the puzzles. That was there was Veneziano, De Vecchia, and then completely cleaned up by Damour exactly what that puzzle was. So the puzzles have all been resolved, and I'm happy to say that these results have actually passed highly non-trivial checks, careful scrutiny. And okay, it's secretly, I'll say, because our techniques are so orthogonal to everybody else's, it's good to see that it actually works. Now, what about going to higher orders? Okay, I won't show you the formulas, but in fact, we went to higher orders for the conservative part. Started first paper at the next order, so there's one more order, g to the fifth. Actually, it's electrodynamics, not general relativity, but it shows that the path forward is clear. And the basic point is the way we think about is we think of it in exactly the same way as we think about electrodynamics. It's the double copy idea. The same problem, the way we look at it in electrodynamics, it's the same problem in gravity. Okay, and so Feynman's observation that gravity follows from the existence of massless spin 2 particles, that's our starting point. And in fact, what we show is that it's a very useful starting point. You can do high precision calculations, state-of-the-art calculations, starting from the concept that gravity comes from a massless spin 2 particle. And we do not use Einstein's equation. How good is it? Well, there's a very nice paper. There are two papers. This one from Damour is where I'm showing you this. So first thing is if you march up in the orders of perturbation theory, so there's first order, second, third, fourth, you'll see that you get closer to the truth, and the truth comes from numerical relativity. Now, just it was already mentioned before, but numerical relativity, it's very expensive, so you can't do this for all the templates or all the information that you need, but you can certainly do case studies, which you then can use compared to perturbation theory. And you can see we're marching upwards order by order. So that looks very good. But in fact, if you use more sophisticated techniques where you absorb this information into what's called effective one-body approach, you can actually do spectacularly well. So this blue curve is using the information also from other papers that include dissipation. And you see the remarkable agreement. So this shows that we are on a good track, and it encourages us to keep on going. Okay, what's the outlook on this? The amplitudes methods continue to have promise. Their use has already been tested for a variety of problems. It's pushing the state of the art, higher orders in G. There's radiation. There's now many papers about using amplitudes methods for radiation. Finite size or tidal effects, many papers on that. Spin is something very active. And the basic point is that the standard quantities of interest in the in-spiral phase, they can be computed in this formalism, and the formalism is go forward. It's far from exhausted. So what's the magic sauce? So the magic sauce is young people, of course. These are, in fact, a list of the young people I've worked with over the years. It's quite a number of people there. In recent years, it's become much easier to attract young people because at an institute, this is the Mani L. Baumick Institute, and thank you, Mani. He's sitting right there. And I can just show you evidence of how we're doing. These are the current postdocs, and Mikhail Salon was young faculty, junior faculty. These are previous postdocs, and there's 2 students. It's quite a collection of really great young people. That's what you need to do great science. Oh, and instead of broom cloth, it's now the problem is to find an auditorium that's large enough. So this is Amplitudes 2022 in Prague. There's Lance, and there's David, and there's me. 222 registered participants. And you can see all the work, all these people are doing a lot of work in many different directions, and I've only scratched the surface in one particular. So summary is the scattering amplitudes, they give us new ways to think about problems of physical interest. Lance and David explained applications to gauge theory, generalized unitarity, bootstraps. Here I discussed a lot the gravitational applications, double copy. It gives us a unified framework for dealing with perturbative gravity theory, and the direct multi-loop calculations become possible in quantum gravity, these very high order computations to understand the properties of supergravity theories. By the way, this search for the ultraviolet properties, it's secretly a search for symmetry. That's what you're actually doing with these calculations. And if you combine the amplitudes methods with effective field theory ideas, it gives us a useful tool for doing gravitational wave physics at the forefront, and I think we can progress in the years. And the story has been long and interesting, and judging from the enthusiasm and energy of the young people that I saw at Prague, the story is definitely far from complete. And before I finish, I should thank my parents. So they were not scientists or engineers. My dad was actually a dental mechanic, but they did have one thing that was very important, and that was the great belief in education. And my dad graduated from university at age 55 because he didn't go to college, and then he was interested in learning, and then he decided I need to go to college. And of course that impressed me greatly. Okay, well, thank you.
Thank you very much. And please. And now I call on stage Marco Pallavicini, Diego Bettoni, which are the components of the executive board of the INFN, and also Fulvio Piccinini, who is the president of the theoretical committee of INFN, who will have the honor to give the award. Up to you. Please, all photos, and please come. Alphabetical.
Indeed. Okay, so thank you very much. And it's an honor to call Swibern here on stage to give him, okay, I cannot handle both the medal and the microphone.
Lance, hello. So I have the honor of giving the Galileo Medal to Lance Dixon. Congratulations to all three winners, and in particular to you. So this is the medal.
Thank you. And now I have the honor to give the medal to David Kosser. Congratulations. Be careful. Congratulations to all of you.
One more picture with the three of you. You can keep the medal without this, otherwise this one. Keep it. Bye. Okay. Okay. Here. Yes.
Mi chiedono di concludere, è stata... Oh, yes, in English, sorry, thank you. So I have been asked by the director to conclude. It's been an honor, it's been a pleasure. Again, congratulations to the three winners on behalf of the INFN, on behalf of the president that unfortunately could not attend, but of course we are very proud of the work you have done, on the contribution you gave to the development of our field, and of course the INFN also with the GGI Institute, which is the main institute devoted to theoretical physics of the INFN, is happy to support and to recognize the work given to science by such good scientists as you. Thank you very much, and thank you to all attended this event. And now, thank you.
Grazie. So thank you, and I hope you will appreciate to close this ceremony with the beauty of music. So I'm calling Matteo Cimatti. Matteo is not here. I'm going to play. Là. Adesso va. I'm sorry. Okay, in the meanwhile, let me thank Marco Benvenuti, the president of the Sistema Museale d'Ateneo of the University of Florence, which includes Villa Galileo, for the kind hospitality. Marco is gone. Francesca Mazzotta and Francesca Cuicchio of the communication office of the INFN. They always did a very good job. And all the GGI staff, I mean, we are not so much. So Mauro Morandini, Annalisa Nichini, and Alessia Tardi for the administrative and technical support. Many thanks to them for this. Matteo is here. Let me briefly introduce Matteo. Matteo is 23 years old. He has recently graduated, obtaining a master's degree from the Haute École de Musique de Lausanne, and is currently pursuing a soloist master under the tutelage of Janine Jansen. That's right. A laureate of several national and international competitions, Matteo enjoys a rich and variety concert activity, both in Italy and abroad, ranging from the solo to chamber performances. So we will listen to him, not here, but in the cloister. That's right? Yes. You want to introduce here your...
Maybe outside.
Um?
Maybe outside?
Outside. Okay, okay. He will introduce piece of... So thank you, everyone, for being here, and enjoy.